Hello, Saturday 4th of May 2024, and I'm ready to start on the last problem of chapter 3. First we must show that these represent right coset representatives for gamma naught in P. We already had something like that, the last problem in section 1, but where we find the left representatives. But then this might just be the inverse of the ones we already found. But let's do it from the beginning. We have gamma and gamma naught of P. And then we project modulo P. That's actually the index I'm about finding, but we already know the index. That's P plus 1. I think it was the function we called theta back in the days of n, which is here P, which is P plus 1. Actually, it was SL2 of Z modulo P Z here. And then this subgroup, and then the index was pretty easy to count. And then, did I at the time argue that these indices are the same? Really? Well, never mind. Well, I can say it depends upon the map being onto. Then it should be pretty easy to see. And we have P plus 1 candidates here. So let's see if gamma j times gamma k may lie in gamma naught of P. So the inverse. And unity. This is not very good. We are dealing with right representatives. Particularly choosing unity here, we get that this lies in gamma naught. Now what's that? We have, it's up to P minus 1, and then unity, of course. I simply missed this obvious one. Well, now let's get back. This one inverse, that's j naught minus 1, 1. Naught minus k minus j. So that means that j plus k must P divides j plus k, and that occurs for a lot of them. And of course, gamma j times the unit matrix fails to lie because 1 isn't What I'll do, I'll go back to the problem of section 1 and find the left representatives and then use the inverse, and then we go on from there. I found the problem. It was actually not the last one, but problem 14. And the left side classes are these, and their inverses, that's right side classes. They are unity, and then S, we just use S, and then K, T to K, the inverses. You know what? That's what they claim here. All right. What did I do wrong? Before going on, I'll just, on a piece of paper, try to do this by hand and not on the tablet, and then check that they are right representatives as they should be. I entered this guy and found the inverse and multiplied by this, and it becomes j minus k. So either I didn't invert it correctly, I couldn't do the matrix multiplication on the tablet. So we are back to the correct right coset representatives. Then we define the trace. Actually, based on some YouTube video I saw, I don't know, quite a while ago, I thought that this was actually the way to define the Hecke operator, and not the way done in the book, but I believe it's something quite different. Now let's look at it. We need to show that TRF is a modular form, provided F is, and there is the transformation, and then the condition at the cusps. And then we just need to state that all gamma does is to shuffle the right side classes. Now, why is that? Well, if we have two distinct side classes, and then if they are mapped to the same, oh, it's right side classes. Then by operating with the inverse of this, we get gamma I, gamma j to minus first. And that means that this guy has to, this matrix has to lie in gamma naught of P. So I equals j. So distinct gammas are mapped to representatives of distinct right side classes, and there's a finite number, so they must be shuffled. That was the transformation. We just get the same sum. Next, the condition at the cusp. Actually, at the rational cusps, that appeared to be easy to me. It's defined that we operate on with any gamma here, and then we make the expansion, and this lies in gamma, so it has the form each addend has the form aj.n q p to nth. So the sum will as well, where n is larger than equal to 0. That's the crux, of course. So the rational cusps are easy. Now, the cusp at infinity, there we need to find out how it actually maps f of z. Let's just forget the identity for the time being. And that's z plus j to minus kth f of minus 1 divided by z plus j, the sum, and that means that the expansion, oh my god, we need to show that only integral values of these q to naught, first, second, etc., so that n is a power of p occurs. And coming from here to the p expansion, that's a little hard. So that idea doesn't work, or else I don't know how to implement it. You know what? It's very similar to what they did in the book, so maybe I just didn't understand it correctly. I'll just try to reread the derivation in the book and then see if I can apply the same method here. Almost as soon as I stopped recording, I got an idea. Let's define a function g of z equals f of z s of k. Let's write z to minus kth. And then operating with that, on that with t to jth, we get this. We know, we didn't really do this. We need to, oh yeah, we needed to do it, I think. Or we could do it with matrix magic. But let's, I'm going back to basics as usual. Let's do it this way. This is the form it has. And now we sum from j equals 0 to p minus 1. It should be p here, yeah. And which of course is the sum d of z plus j and this is when we use zj, it's 2 pi I z plus j pth. So it gives e to 2 pi I j divided by p, qp. And when we add over this, we only get contributions when j is a multiplum of p. P divides n. So we sum over the n's, giving multiply of p, and then it gives p, of course, and then qp to n, and since it's a multiple, yeah, then we only get integer coefficients. So that's the cusp condition at, I think it's 3,8, that it's actually a series in q to the nth, not any rational roots. That actually finishes part B, doesn't it? cusp conditions and the transformation law. Right. And see if f, that seems trivial. Then all the sums give the same here, and there are p plus 1 addends, so that's trivial. Now what's the last one here? Alrightio. Oh, so they are connected. All right. So I wonder if we, instead of using gamma, uses gamma naught of p and gamma 1 of p here, if it still works all the machinery. Oh, but it only happens if it's a modular form in its own right. Now, what is Tp of f? It's f of p set plus, isn't it? Or am I wrong here? Plus, yeah, maybe it's only this sum. I'll just need to check that. It's actually in the book. Well, I couldn't remember it. It's formula 515. With chi being trivial. And then it's 1 divided by p, and then this times p to k minus first. So that was the so the right-hand side. That's not nice, but we'll just finish it here. P we multiply with p to 1 minus k halves. That's p, yeah, that must be multiplied here. And then we get p to minus k halves f of p z plus p to k halves f of z plus j divided by p. That makes sense to me. Right. And we have to compare this with this expression. I'll have to do that on the next page. So let's work on this. this we can do p to minus. The determinant is p to so the determinant to plus k halves, and then p set plus d, that's p set, so it's k to minus, and then z to minus k halves. Z to minus k's. Oh, where was f? Oh, that comes afterwards. Now, f actually is a modular form of gamma itself. This is not necessarily, or is it? I think this is the wrong way. I think we should do our matrix magic. So let's use the definition. Trace f of k equals the sum and then we use the gamma k. We just take the unit matrix out. Yeah, we do that afterward. That is 0 minus 1, 1, j plus we multiply those two matrices. I don't hope I need to do that on Maple again. Minus 1 minus j 0 minus p I wonder if this shouldn't be we'll just put minus outside. If we do this, then it's 1 j 0 p. Let's just write t to jth. Actually, I would like to have p to the 8th first. Oh, actually, t to the 8th, that's exactly what we need. Now, we are working on this left-hand side and must simply find the expression. So let's put a z on it. And this was an in between. Oops, z. Yeah. Now, the determinant of this guy is p. So it's p to k halves and then p to minus k. That's k to minus p halves. F, and then the sum, of course. Don't forget the sum, you moron. F of 1 divided by pz. No, 1 divided by, yeah, what's that? Now, where's z? That was a little weird. Z divided by p. Oh my god. Z divided by t, and then z plus j divided by p. Yeah, plus, and then this is pz. The determinant is p, so it's p to k halves. So it's p to minus k halves, and then z to minus kth, f of 1 divided by p. Z to be compared with this, and we are not very close. This is quite close. There's just a factor here, but the other expression, that's very weird. Oh, I think actually that it's the same. By the same trick we already have used several times. this trick. So I'll just look at that. Another thing I would like to do is actually to compute the trace of some of the modular forms we have on gamma naught of 3, like M3 of gamma naught of 3, where we should have a modular form. If we use it on gamma naught, so yeah, we'll see. I'll try to use it and see what it gives, and then hopefully show you where, if this does give what I think, and find the mistake here. Hello there, it's now Sunday, and I just wanted to show the work before I'm going to dinner. I've found a general formula for the trace of gamma 1 function of modulo n and order k, of modulo p, no, of level p and weight k. So we have the series expansion, and then we need the series expansion on the cusp at 0, or any cusp would do, of course. And then the trace is given by this formula. And I wanted to do a few examples. First, I considered the function I, so to speak, discovered myself. Of course, it's been known for at least 50 years. So, but I don't know the expansion at the cusps. Of course, the trace of this guy should vanish, so we could compute the value of one of each 3 coefficients in at the cusp at 0, but leave that. Now, another example was the function of weight 2, which I found on the internet, and the trace, of course, must vanish because there's no modular form for the full modular group of weight 2. And it takes a little work, and then due to this formula, which I believe is well known, but I forget it, so I have to derive it every time anew, then it vanishes. Then I took this one, which followed from a corollary to, I think it's proposition 17, I'm not sure, which lies here. So it's given by this expansion, and G, we have had that a lot of times, so it's just inserting set third instead, because E4 is invariant under S. Then I get this expansion, and now it's just applying this formula to the trace. And then when we use this with, here k must be 3, so it's a little confusing, of course, that I use k for the weight and then also for the power of the roots. But then I got this, so the trace of f here actually is the function it came from, E4 of z times a constant. So that finishes my work on chapter 3. So have a nice summer holiday, and I'll see you again in September when I start on chapter 4.